Okay, we're looking at number 3 from the 2013 AP Physics B exam. This is primarily going to be a refraction optics problem, and we're taking a laser beam, shining it on a flat surface and measuring the angles of incidence to the angle of refraction. As we vary that angle of incidence, the angle of refraction varies. The laser has a given wavelength. It is going to be red. It is going to shine from air to my new medium, and ultimately we want to figure out the index of this new medium. What is the n value inside this substance? So we've got the various different data points taken, your initial angle of incidence 0, 15, 30, 45, 16, 75, and as we increase that angle of incidence to the normal line, we have my angles of refraction. Conveniently, we've also figured out already ahead of time the sine of each of those angles. And for part A, we want to basically create a graph that will allow us to determine the index refraction of this plastic such that we are going to use a straight line that represents the data. Ultimately, we're saying what is the n value that comes from a straight line that we graph. So let's look at Snell's law. That's going to help us figure out what we should graph. N1 sine theta 1 equals N2 sine theta 2. And N2 is ultimately what we want to find. And since we're looking at a straight line, well, that indicates to me slope. And the slope of a line is a value over another value. And if we're looking for n, I'm going to divide theta 2 to show that n1 sine theta 1 divided by sine theta 2 must be my n value. And since it's going to be a value over value, I know that this top number is what I need to graph on my rise, or my y dimension. This bottom is what I need to graph on my run, or my x. Since n1 is the original index and it started in air, n1 is going to be 1 the whole time. So we can basically ignore n1. And ultimately, we need to graph sine of theta 1, which is sine theta I on my data table, versus sine theta 2, which is going to be sine theta r. So sine theta r comes down here. And if we look at my data, I go 0 to 0.97, 0 to 0.7. I think it's logical to just graph all the way up to 1 on each dimension. And I've already figured this out ahead of time. There are 10 boxes, so each one will represent 0.1. So 0.1, 0.2, etc. I'm going to complete the graph and... Okay, before I put the data points in and create my best fit line, I want you to see the axes I created simply again just by 0.1 increments. 0 is at the origin. Alright, I'm going to pause it again, do the data. Alright, here are my data points. I didn't take excruciating detail for this. It's kind of hard. The print is not perfect, but you get the general trend. It certainly looks linear. I'm now going to go ahead and put my best fit line. We do have data points given as 0, 0, so that best fit line should start at 0, 0, and it needs to correspond to the majority of the points, or the average of those points, which looks pretty much like this. Everyone's going to have a slightly different best fit line, but it's going to be in the right general region. This is part A. Everything's covered, everything's clear. Now let's move on to part B. Well, actually, part B is where we need to draw the straight line. So I've done the straight line. Now I want to use the slope of this line to determine the index refraction of the plastic. Recognize that slope is literally just the y over the x. So for this, I would definitely indicate that you know slope is change in y over change in x. And then pick two data points that are on that line. Don't pick the points from your data table. Pick the points from this best fit line. And so I'm going to circle the points that I think are the clearest and easiest to read. Because we started at the origin, we could use that. I'm not gonna, for the sake of example purposes. I think this is a nice clean one that looks like it crosses a pretty clear spot. And at that point, I'm just going to have to pick something that crosses. I like to pick one that crosses directly in line with at least one data point. So this one is directly in line with at least one data point. So this is what I'm going to use as my rise over run. Do not circle them. Do not change your graph on the AP exam. Do not draw these dashed lines in like I'm doing. I'm just doing this to point it out to you folks. Rise over run. So my change in y is going to, well, it finishes at 0.7. It starts off at looks like 0.42. So I'm going to do zero point 0.7 minus 0.42 for my change in y. And then my change in x, it finishes at zero point 0.5. It started at 0.3, so I'm going to do 0.5 minus 0.3. I think it's also very important to show this work. That way you can prove that you are indeed using your data values from the graph. Alright, I'm going to calculate this, be right back. Alright, when I do this, I get a value of 1.4. Now that's going to vary. Everyone's going to have a slightly different index. So there's a given range of acceptable answers for this problem, and they will accept anywhere from 1.2 to 1.6. So perhaps your line is not quite as steep or steeper, so your index will vary a little bit. Part C, we want to now, the student wants to confirm the results from Part B by taking it and using a slightly different experiment. We now want to use the critical angle. So we need to describe one experimental method the student can use to measure the critical angle. And then we want to indicate how the index of refraction can be determined from that measurement. There's multiple directions you can take on how to start off this problem. For the sake of explaining it to you, I want you to understand that n1 sine theta 1 equaling n2 sine theta 2 is still going to be true here. However, there's going to be a little bit of a catch, because recognize, and I'm going to just kind of fictitiously draw something, if I have a medium in which something is being incident on, if it's at the critical angle, it'll refract so that it refracts perpendicular to my normal. If it's greater than my critical angle, it will stay inside. And if it's less than that critical angle, it'll refract outward. So that critical angle comes into play by recognizing that n1 sine theta 1, this initial index and the initial index of refraction, angle of incidence, must equal n2 times theta 2, but theta 2 is, well, times the sine of theta 2, but that's sine of 90, and the sine of 90 is 1. So, the critical angle is always going to equal n1 times the sine of theta 1. There's one key thing you got to understand. It always needs to originate from a more dense medium entering into a lower dense medium. So it can't go air to the plastic. It has to go the plastic to the air. Keep that in mind when I explain this experiment. To explain that experiment, I want to go all the way back up here and look at my original experiment. And now, instead of shining the light from air to the plastic, I'm going to take that light and shine it this way. What I'm going to do is I'm going to shine it straight on to first show that it'll go straight through the plastic and straight back into the air with no refraction. And then I'm going to increase that angle. I'm going to keep doing that. So I'm going to increase this angle, and then so now it's going to slow down a little bit, and then it's going to speed up. And I'm going to continue to do this until I get a very clear refracted critical angle. What does that mean? Well, ultimately, if it's going along this medium boundary, you're not going to see it. You're going to increase this angle here until basically there is no light at all. Any angle bigger than that, that light will eventually stay inside the glass, and so you might detect light exiting that plastic over here. And anything less than that angle, you will get refraction, so you're going to determine light existing up here. So when you're setting up your experiment, you need to indicate the following. First, you need to indicate that you need to shine that light straight on from the curved side of the dish. Why the curved side? Simply because we need that light to go from the plastic to the air and not the air to the plastic. You need to increase that angle of incidence until we see no light. That'll therefore be your critical angle. At that point, you need to refer to the equation that we looked at earlier down here. The index in the second medium must equal the index in the first medium times the sine of that critical angle. The critical angle is what you just measured. The medium in which it originated is what we're looking for. So you will need to indicate that the index of the medium that we're looking for will be equal to the index of the medium in which it is going to, divided by the sine of the angle that you just measured, which is the critical angle. Well, since n2 is air, it's simply going to be 1 divided by sine of the critical angle. And that is it. That completes number 3 for the 2013 AP Physics exam.